Hello, folks. There has been a video segment on every chapter, just about every chapter of the FEA tutorial book, except for chapter 21. Now, in fact, some of the chapters there are multiple video segments. They may have been done at different years, and they may have covered different items, but the only one that's missing is this adaptive refinement. So let me tell you first of all what the idea behind this chapter is, what this process is. Suppose we have a structure like that, a very simple part, and this left end is clamped, and the right end, this circular hole, is subjected to a bearing load. Okay, as you can see in the direction, in the axial direction. Now, it is the case, we know that the critical area for design purposes is in the vicinity of the circle. Somewhere around the circle, the stresses are very large, okay? Or the stress gradient is very large, and that is a critical zone. And what we need to do is to select a fine mesh in that area to be able to resolve this stress gradient. Now, of course, if we know where that thing is, if we know where that area is, then we can go ahead and refine it and keep refining it until a mesh convergence, in our opinion, in our judgment, has been achieved, and we stop it there. Okay. But the more systematic approach is let the software refine the critical area, okay? And this is what is called adaptive refinement. And then it measures an entity, which in the case of Catia will be the strain energy density. And when the strain energy or strain total, maybe total strain energy reaches a threshold value, below it reaches something a threshold value, and it doesn't change very much from that point on to within some percentage specified, then the software stops refining. Okay, so let me go ahead and model this problem. Let me start with a part file, and since my units are in inches and pounds, I'm going to set my default units. So let's go to Tools, Options. Okay. And under parameters and measures, under units, I'm going to change my length to inches, and my pressure, which means the stress, to psi. Where is it? Right there. And the force, or the force right here, 2 pounds. Okay, now if you look at the problem that we've got at hand right there, the dimensions are given. The dimensions are given in the chapter: 4 inches, 3 inches, half an inch radius circle, and the thickness one is made of aluminum. But this problem does have actually two planes of symmetry. You can cut it along the length, and you can slice it in the middle. So you need to really take 1/4 of this model and put surface slider. But I'm not going to do that. In the book, the symmetry is not taken into account, or is not used. Okay, let's go ahead and do it. On that plane, I will sketch that profile. We're going to clean it up in a minute. Do something like this. I don't want this thing to snap to the grid point, so I'm going to uncheck that. All right, now let's dimension it. Well, first of all, we're going to make it symmetric, the top and the bottom. Top, control bottom, control middle axis. Let's make it symmetric, although that is not necessary because we're not using symmetry properties at all. Okay, and then we'll put some dimensions here. I believe this was 3 inches. It should be 3 inches. And let's see now, this length 4 inches. So dimension from this to that, 4 inches. Okay, let's draw our circle. Radius 1/2 inch. Right there. Dimension this thing to be 1/2 inch. Or diameter 1 inch. Okay, exit. And we pad it. In both directions, mirror extent. Total length of 1 inch, which means 1/2 inch specified over here, and that makes the total thickness 1 inch. Okay, good. So let me change the rendering here. All right, now let's make this thing out of aluminum. So apply material, metal, aluminum on the part, and we say okay. We're pretty much done here. So let me save, file, save management, save as, desktop, new folder, adaptive refinement. Adaptive refinement. Okay. Now, if we go to analysis and simulation, generative structure analysis, Catia will immediately mesh this thing. And let me actually, what I'm going to do is, I will use linear elements, so I don't know what the default was here. Let's check that. So double click on Octree linear. Okay. So the default mesh is drawn here for you. If I want to look at that, what is it? A mesh visualization. There we are. Okay. Now, now it's obvious that you need to refine the area here, and it is possible to do that manually, but that's the whole purpose of adaptive refinement is to avoid doing this manually. Just to remind you how this is refined manually. So you just go to this icon, the icon over here, local mesh size, and you select the area that you want to refine. It uses a size that big. You can change that. For example, I can change this into 0.2 or 0.1. Notice it's a lot smaller right there. And if you look at the mesh, right click mesh visualization, it's going to be like that. Okay, it's finer in this area, but elsewhere it's a bigger size. So what I'm going to do is I'm going to actually delete this. I'm going to delete this local mesh size because we don't want to do it manually. Now let's apply our loads and restraints. So the left end is clamped. This left side is clamped, and this face. So under the load, let's find the toolbar for the load. Right here, it's a bearing load, and the bearing load is, I believe, right here. Bearing load on that face in the direction Y. The way I've drawn it in direction Y. 1,000 pounds. Now, mind you that in the book, the way I've constructed this may be different, so that I may have applied my load in the X direction, but that depends on how you make your model. Now, we can run this, and it's going to, of course, produce results, but the results are going to be very iffy, mainly because, first of all, you're using linear element, and we're not using any refinement in places where actual refinement is needed. But let's go ahead and run it anyways. So, right there. It's going to be fast. There we are. Let's look at our uh, displacement. Needless to say, it's going to look like that. You can animate it. Of course, that makes sense. So qualitatively it deformed correctly. Now look at the stress distribution, looks like so. So let me change the rendering to material shading. Okay, now you can already see that there's some kind of a, these elements are too big. That's why this is supposed to be a lot smoother, and I have no confidence in these values. Okay, so right now it says that the biggest stress is that red area, which is around what is this 1,270 pounds, which is, I mean, obviously very small, but still the maximum value is predicted to be 1,270 psi. Okay, so first of all, let's deactivate this. All right, now if you go under, find the icon which says adaptive refinement. So I'm dragging this thing out. Let me put it there so that I can't remember what the name of this toolbar is. But anyway, it's right there. It probably says adaptive refinement. Yeah, right there. Put the cursor on it. It says new adaptivity entity. You click on it, and it asks you a couple of things. First of all, where is the support? In other words, which element is it that you want to refine? Because it could be that, for example, you're dealing with assembly and there may be several of these. Okay, so in this case, there's a single part, and this is what I want to basically refine. This is the support. You select it, and then it says, okay, what is the objective error? Now, what I'm going to do is the smaller this thing is, the longer it's going to run, and obviously, uh, in principle, the more precise it's going to be. I don't say accurate because accuracy also has to do with the modeling aspect. Now, by the way, look at what it says here. Currently, the error is estimated to be 25%. Okay, so let us change this to let's make it 10%. Let's try to push it to 10% error. So we say okay. Uh, Anything else we have to do? No, I guess not. There we are, and let's run it now. So this will iterate. Oh, there was something else that I could have done. Let me go ahead here because I think I prematurely closed that. Where is that adaptive refinement right there? Double click on it. Uh, yeah, dashboard solution. Okay, that's fine. Let me just check something because it looks like we can also specify the number of iterations. It's just that I don't remember where that is to be specified. Just bear with me for a second. Uh, there is a, let me see. Well, I think once we try to run it, it will ask us about the number of iterations. So let's try to run it now, right? Oh, here, that's what I meant. Okay. So when we try to run it, ordinarily we use this calculator type thing, compute, but this one says compute with no with adaptivity. You click on it, and this is where it's going to ask us how many iterations should it do before it gives up. So let me make this thing 10 iteration. Allow on refinement, of course, that's self-explanatory. In other words, it will actually let the elements become bigger. I'm not going to do that. And this one is the minimum size. In other words, if it falls below this size, it will not refine it. If the element size falls below this, we'll not refine it. We say okay, and let's let it run. If you put a tiny number as far as percentage error, you might get a lot of iterations, and then it will stop and say it didn't finish it, but this is the current status. I think this is good enough. It'll run very quickly. There. So, let's see. You click on the von Mises stress, and notice that it went from 1,270 to 1,740. And notice that how much nicer and smoother the variation of the stress is around this circle. Okay, and let's check something by the way. I'm going to double click on this global adaptivity. Notice that right there. See that? It went from 25% error in estimated in the energy density to 9.69, and it stopped. Actually, we asked it to be a target of 10%. All right. So that's pretty much it. It's fairly easy to use. It's just that make sure you don't put tiny numbers so that this will take forever. Good luck.